This video will help you fill out the notes for Chapter 5, Section 1 about factoring integers. And then at the end of this video, I'll also include solutions to the assignment that you'll do on line paper. So number 1, read the top half of page 185 about factoring integers. So you're in your Chapter 5 textbook today, the first section, and taking a look at the first paragraph, we can find out what it means to factor an integer. It gives us an example, 56 equals 8 times 7. And then it also says 56 is equal to 4 times 14. There are other pairs of numbers that multiply together to make 56. Those numbers that multiply to make 56 are called factors of 56. Factoring the number 56 means to write it as a product, to write it as a pair of numbers multiplied together that make 56. So we see the definition of the word factor in the paragraph. Factoring is writing as a product of numbers. So number 1, check. We read what it means to factor an integer, to write as a product. Now number 3, true or false. The type of numbers that you use to factor an integer is called the factor set. That is true. In the example that we looked at in the book, where the number 56 was written as 7 times 8 or 4 times 14, the 7, the 8, the 4, the 14, those were positive integers. So it looks like in that example, the factor set was the positive integers. Now number 4, read example 1 on page 185. Give all the positive factors of 56. The authors have worked out the solution, finding every single positive number that divides evenly into 56. To find the answer, they progressively divided 56 by each positive number starting with 1. So 56 divided by 1 gives them a pair of factors, 1 and 56. The number 1 and the number 56 are factors of 56. Dividing 56 by the number 2 gives another pair of factors, 2 and 28. 2 and 28 are factors of 56. When the authors tried to divide 56 by the number 3, it didn't work out evenly. It made a decimal. So 3 is not a positive factor of 56. The authors then tried 4. 4 divides into 56 14 times. So 4 and 14 are factors of 56. 5 didn't work, 6 did not work, but 7 divided in evenly. 7 times 8 is 56. Now, when the authors try the next number after 7, which is 8, they would end up getting the same pair of factors that they just discovered, a 7 and an 8. So they stopped at that point. So the positive factors of 56 are the numbers 1, 2, 4, 7, 8, 14, 28, and 56. They are the only positive numbers that divide evenly into 56. So we have looked at example 1. Now number 5, true or false. To identify positive factors of a number, you divide the number by all of the positive integers to see which ones divide in with no remainder. That is true. Now that sentence describes how you find factors of a number. Let's try this. Number 6. List all the positive factors of the number 24. Start with 1 and divide 24 by 1. You get 24. So 1 and 24 are factors of 24. Now try 2. Does 2 divide evenly into 24? Yes, it does, making 12. So 2 and its counterpart 12 are factors of 24. Now try 3. 3 divides into 24, creating 8. So the number 3 and the number 8 both divide into 24. Try 4. 4 times 6 is 24. Now try 5. 5 does not divide evenly into 24. If you type that in your calculator, you get a decimal. The next number after 5 is 6, but notice how we've already got 6 in our list, so we stop. So all of the numbers listed on the screen are factors of 24. You can leave them in this order here where they're written in pairs, or if you want to, you can list them in increasing order. Now question B, what are all the positive factors of the number 11? Well, start by dividing by 1, and you'll find out that 1 and 11 are factors of 11. Now, if you try to divide by 2, you'll get a decimal. If you try to divide by 3, you'll get a decimal. If you try to divide by 4, you'll get a decimal, and so on. And eventually, you'll get all the way up to 11, which you've already have in your list. So for this number, 11, there are only 2 factors, 1 and 11. Question C, list all the factors of 120. Start by dividing by 1 and find out the counterpart to that, which is 120. Now divide by 2, and you'll find out 60. Now divide by 3, and you'll get 40. Now divide by 4, and you'll get 30. Now divide by 5. The number 120 ends in a 0, so it should divide evenly by 5, and you'll get 24. Does it divide by 6? Well, yes, it will, because it divided by 2 and by 3, and so we know it's going to divide by 6. And that makes 120. Now try dividing by 7. You'll find out it doesn't work out evenly. Does it divide by 8? On a calculator, if you'd go 120 divided by 8, you'll get 15. So we need to add 8 and 15 to our list. 120 will not divide evenly by 9, but it will divide by 10, creating the counterpart number 12. And 120 does not divide evenly by 11. After 11, the next number you would try is 12, and that's in our list, so we can stop. So on screen, you have all of the factors of 120. Number 7, read about prime numbers below example 1, and then explain what a prime number is. A prime number, or prime, is an integer greater than 1 that has no positive integer factor other than itself and 1. The first 10 prime numbers are the number 2, the number 3, the number 5, the number 7, the number 11, the number 13, the number 17, the number 19, the number 23, and the number 29. These are prime numbers because the only factors of each of these numbers are 1 and the number itself. The 11th prime number is the number 31. So number 7, explain what a prime number is. A prime number is a number whose only factors are 1 and itself. Number 8, yes or no, 8 is a prime number. Does 8 divide only by 1 and 8, or is there another number that divides evenly into 8? This answer is no. 8 is not a prime number because it's also divisible by 2 and by 4. Number 9, is 17 a prime number? Yes. 17 is only evenly divisible by 1 and itself. Number 10, list the first 15 prime numbers in increasing order. Well, 10 of them were given in the book. You can copy those, but then you'll have to find the next 5 of them. And here they are. The reason it's important to know several of the prime numbers, to either have them memorized or have them written down in notes where you can quickly find them, is so that when you're asked to factor a number in algebra, that you know when a number is prime and is not going to have any factors. Otherwise, you're just wasting your time continuously dividing by numbers only to find out that nothing is going to work. Number 11, true or false? If you write a number as a product of prime numbers, then you've written its prime factorization. This is true. Number 12, true or false? The prime factorization of the number 45 is the product of these prime numbers, 3 times 3 times 5, which can be written in exponential form as 3 to the second power times 5. Well, what you want to do to check if this is true is, first of all, do the numbers actually multiply to 45? 3 times 3 is 9. 9 times 5 is 45. So the product makes 45. Is the product built from prime numbers? Yes, it is. 3 and 5 are prime numbers. This is true. Number 13, true or false? The prime factorization of the number 24 is 2 to the second power times 6. Well, 2 to the second power is 4, and 4 times 6 is 24. So the product correctly makes 24, but the product is not made from only prime numbers because the number 6 is not a prime number. This is false. The correct factorization of the number 24 is 2 times 2 times 2, which is 8, times 3. This factorization makes 24 and is made from only prime numbers. Number 14, study example 2. Find the prime factorization of the number 504. And the authors show how to do this. Start with the number 504 and divide it by the first prime number from your list of primes that you wrote in your notes earlier. That first prime number was the number 2. Find out if 504 divides evenly by 2. And it does, creating the number 252. Now take the number 252 and try to divide it by 2. Well, that works as well, creating 126. Now divide 126 by 2, and you'll find out that 2 times 63 is 126. Now, if you try to divide 63 by 2, it's not going to work. 63 is not an even number. It won't divide by 2. So try the next prime number in your list from your notes, which is the number 3. And you'll find out that 63 does divide by 3 evenly, creating 21. Divide 21 by 3, and you'll find out 7. At this point, it's helpful to recognize 7 is itself a prime number, and so there's no point in trying to further divide the 7. It's not going to work. So if you have carefully kept track of your factors like the authors show, using this technique called a tree diagram that sort of branches as you move downwards, you can now see the prime factorization is 2 times 2 times 2 times 3 times 3 times 7. All 6 of those numbers multiply to 504, and they are all prime numbers. And then in exponential form, you see that same answer written a little bit quicker. So we have examined example 2. Check. Number 15. To write the prime factorization of a number, you divide that number by prime numbers in successive order until the number is written as a product of only prime numbers. Check. That is how you do it. Number 16. Let's try this skill. Write the prime factorization of the number 32. First thing to try is 2. 2 is the first prime number. Does 32 divide by 2? Yes, it makes 2 times 16. Now take the number 16 and try to divide it by 2. Yes, that makes 2 times 8. Now take the number 8 and try to divide it by 2. Yup, it still works, 2 times 4. Now take the number 4 and divide it by 2. 2 times 2. At this point, the end of every branch is a prime number. And we can create our prime factorization from this tree diagram. 2 times 2 times 2 times 2 times 2 is 32. There are 5 2's. So a quick way to write the answer is 2 to the 5th power. Now let's do this with the number 80. 80 is an even number, so we know it will divide by 2. It's 2 times 40. 40 is an even number. It divides by 2. So 2 times 20. 20 is an even number. It divides by 2. 2 times 10. And 10 divides by 2, creating 2 times 5. And 5 is a prime number, so we don't need to try to further divide it. 80 is 2 times 2 times 2 times 2 times 5, or 2 to the 4th power times 5. 2 to the 4th power is 16. 16 times 5 is 80. Now 75. 75 is an odd number. It will not divide evenly by 2. Try dividing it by 3. It makes 3 times 25. Now, what can you divide 25 by? I mean, you can try to divide it by 3 again. It's not going to work. The next prime number after 3 is the number 5, and you'll find out 5 times 5. You can see already that knowing your multiplication facts is very helpful here so that you're not wasting your time trying to think of numbers that divide into 25. Okay, we have 3 times 5 times 5. So 3 times 5 to the 2nd power makes 25. Number 17. Read the top of page 186. Exponents are generally used for prime factors that occur more than once in a factorization. The prime factorization of an integer is unique. The word unique here means there is only one prime factorization for any integer. A factor of 2 or more integers is called a common factor of the integers. The greatest common factor, GCF, of 2 or more integers is the greatest integer that is a factor of all of the given integers. So this paragraph introduces the idea of common factor and a vocabulary term, greatest common factor. Number 17, check. Number 18, the numbers 8 and 12 have common factors. What are their common factors? What are the factors of 8 that are also factors of 12? What are the numbers that divide evenly into 8 and those numbers divide evenly into 12? Well, let's factor 8. 8 divides by 1, and by 2, and by 4, and by 8. Now let's factor 12. It divides by 1, and 2, and 3, and 4, and 6, and 12. What are the common factors? The factor 1 is in both lists. The factor 2 in both lists. The number 4 is in both lists, but the number 8 is not in both lists. The common factors are 1, 2, and 4. These are the 3 integers that will divide into 8 and divide into 12. Number 19, yes or no? Do the numbers 21 and 40 have any common factors? 21 divides by 1, 3, 7, and 21. The number 40 divides by 1, 2, 4, 5, 8, 10, 20, and 40. Are there any numbers common to both lists? Yes, the number 1. And so the answer is yes. There is a common factor between 21 and 40, the number 1. Number 20, when 2 or more numbers have common factors, then the largest of those common factors is called the greatest common factor, or GCF. Number 21, in problem 18, what is the GCF? So problem 18, we had done it earlier, and we found out that there were 3 different numbers that are common factors, the 1, the 2, and the 4. Which is the greatest? The 4. 4 is the largest number that divides into 8, and it also divides into 12. Now in number 19, what is the greatest common factor? Well, the only common factor was 1, so I guess it must be the greatest common factor. Number 23, study example 3. What is the first step to find the greatest common factor of 2 numbers? The authors suggest finding the prime factorization of each integer. Then form the product using the smaller powers of each common prime factor. This is a different technique than what I did on the 2 previous examples in the notes. I made lists of all of the factors, and then I simply looked for the greatest one that was common. The authors are suggesting a different technique. Now, either method works. It's just sometimes listing all the factors might take a long time, whereas finding the prime factorization might be quicker. But then there's other times where it maybe won't take too much time to get all of the factors listed and then simply look for the largest one. So here's what the author suggested. Write the prime factorization of each number. And then once you have that written down for both numbers, then there's something you're going to do to that as your step 2. Now, the alternative first step, remember, is simply just list all of the factors, find the ones that are common, and then select the greatest. Number 24, find the greatest common factor of the numbers 32, 40, and 60. What is the greatest number that's a factor of each of those? What is the greatest number you can find that divides into all 3 of those numbers? Well, they all divide by 1, but is there something greater than that? That's what we're interested in figuring out. If we use the author's method, then we would find the prime factorization of each number. So 32 is 2 times 16, 16 is 2 times 8, 8 is 2 times 4, and 4 is 2 times 2. 32 is 2 times 2 times 2 times 2 times 2, or 2 to the 5th power. You can probably see that the more powers you memorize, the easier algebra class will be. For instance, I knew that 32 was 2 to the 5th power. I only wrote out the tree diagram for these notes. Okay, now the number 40. 40 is 2 times 20. 20 is 2 times 10. And 10 is 2 times 5. 5 is a prime number. So 40 is 2 times 2 times 2 times 5. 2 to the 3rd power times 5. 2 to the 3rd power is 8. 8 times 5 is 40. Now the number 60. 60 is 2 times 30. 30 is 2 times 15. And 15 is 3 times 5. 2 times 2 times 3 times 5 is 60. I have the prime factorizations of all of the numbers. Now the second step is to find the common factors and then use the lowest power of those common factors. The number 2 is a common factor. It appears in this list, and this list. What is the lowest power of the number 2 that appears in any of the lists? That's in this last one, 2 to the 2nd power. 2 is the only common factor in all lists. The number 40 has a factor of 5, but the number 32 does not. The number 60 has a factor of 3, but the number 32 and the number 40 do not. The only common factor is 2, and the most 2's that we're able to use is 2 to the 2nd power, because the number 60 only has that many 2's. By the way, 2 to the 2nd power is 4, and that's the greatest common factor. The largest number that divides into 32, 40, and 60 is the number 4. Now it's pretty simple to find the common factor, to notice that that's a 2. That's in all the lists. The thing that students will often get stuck on is the idea about using the lowest power of that 2 that appears in all the lists. You can't use the highest power because even though 2 to the 5th power divides into 32 for the number 32, the number 40 does not divide by 2 to the 5th power. The number 60 does not divide evenly by 2 to the 5th power. You can't say that's the common factor. 2 to the 5th power, which is 32, is not a common factor. But using the lowest power of the 2's that appears, which is the 2nd power, makes the number 4. 2 to the 2nd power is 4. 4 does divide into all 3 of the given numbers. Number 25. When answering number 24, after you write the prime factorization for each number, what do you do next to get the GCF? We used the lowest power appearing for each common factor. The only common factor that appeared was the numbers 2, and the lowest power on that 2 was 2 to the second power from the number 60. Thank you for filling out the notes with the help of this video. Next, you have a lined paper assignment which you'll complete and staple to the back of your notes and turn in to the substitute teacher just like you always do. The assignment is given here on screen. Page 186 of your Chapter 5 textbook PDF, and it's this list of odd-numbered questions. Here's a solution guide to help you with the assignment. So you can use the solution guide while you're working if you need to, or better would be to try all the questions on your own and then consult the solution guide to see if you've done them correctly. Number 1, we're given the number 13, and the directions ask us for all pairs of factors of each integer. Now it's important to consider factor set here so that we know what numbers we're even supposed to consider. We're going to assume that the factor set is the integers unless we're told differently. So we're looking for integers that divide evenly into 13. One pair of integers is 1 and 13. But if 1 times 13 makes positive 13, then so does negative 1 times negative 13. So these four numbers are the integers that divide evenly into 13. Next, number 3, 24. Let's do what we did in the last problem and first list all of the positive numbers that divide into 24, and then we can give the negative numbers. So 24 is 1 times 24, or 2 times 12, or 3 times 8, or 4 times 6. 5 does not divide evenly into 24. Now, if those positive number pairs make positive 24, then the negative counterparts will also multiply to make positive 24. So negative 1 and negative 24. Negative 2 and negative 12. Negative 3 and negative 8. And negative 4 and negative 6. This list of 16 integers are all of the integer factors of 24. Number 5, 29. 29 is a prime number. It only divides by 1 and itself. So 1 times 29 makes 29. But if we include all integers, which includes negatives, then negative 1 and negative 29 also are factors of 29. Number 7, 40. 1 times 40, 2 times 20, 4 times 10, and 5 times 8. And then the negative versions of these. This list of 16 numbers are all of the integers that are factors of 40. Next, number 9. The number is negative 121. So one way to multiply two numbers together to make 121 is 1 times negative 121. The counterpart to that pair would be negative 1 multiplied by positive 121. Now, 121 is an odd number, so it does not divide by 2. Does it divide by 3? Take a calculator and go negative 121 and try to divide it by 3. You'll find out it does not divide evenly by 3. If you add the digits 1 plus 2 plus 1, that adds up to 4, which is not a sum that's divisible by 3. So 121 can't divide by 3. 121 cannot divide by 4 because it didn't divide by 2. 121 does not divide by 5 because it doesn't end in 0 or 5. 121 does not divide by 6 because it didn't divide by 2 and 3. Does 121 divide by 7? No, it doesn't. If you type that in a calculator, you'll get a decimal a little bit larger than 17. 121 will not divide by 8 because it didn't divide by 2. 121 will not divide by 9 because it did not divide by 3. 121 can't divide by 10. It doesn't end in 0. 121 does divide by 11. Negative 11 times positive 11 makes negative 121. Now, for this particular pair of numbers, there's no reason to write a counterpart pair below because I've already written the pair of numbers negative 11 and 11. So these 6 integers are the factors of negative 121. Notice here that knowing your multiplication facts is very helpful. If you know that 11 times 11 is 121, then you're more quickly able to get those 11s in your list. Next, number 21. Given the number 16, write the prime factorization of 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. 2 times 2 times 2 times 2 is 16. So 2 to the 4th power is 16. Number 23. The number is 69. 69 does not divide by 2 because it's not even. It does divide by 3 because 6 plus 9 is 15, and that sum divides by 3. 69 is 3 times 23. 23 is one of our prime numbers from the list in our notes, so we can't further split up 23 with a branch. So the prime factorization is simply 3 times 23. Next, number 25. The number is 75. 75 is 3 times 25, and 25 is 5 times 5. 3 times 5 times 5 is 75. So that's 3 times 5 to the 2nd power if you write it in exponential form. Number 27. The number is 27. 27 is 3 times 9. And 9 is 3 times 3. 3 times 3 times 3 is 27. So the prime factorization is 3 to the 3rd power. That's another good one to memorize. The more powers of 2 that you memorize, the more powers of 3 that you're able to memorize, it'll make algebra class easier for you. Number 29. The number is 99. Well, 99 is not an even number. It won't divide by 2. It does divide by 3. 3 times 33 is 99. Now try to divide by 3 again. 3 times 11 is 33, and 11 is a prime number. 3 times 3 times 11 is 99. Number 31, the number is 104. That's an even number. It's going to divide by 2. 2 times 52 is 104. 52 is an even number, so it'll divide by 2 again. 2 times 26. 26 is an even number. 2 times 13. And 13 is a prime number, so we stop. 2 times 2 times 2 times 13 is 104. Number 33. The number is 125. Well, this divides by 5. 5 times 25 is 125. And 25 divides by 5. 5 times 5. 5 times 5 times 5 is 125. Number 35. The number is 450. That's an even number, so it divides by 2 for sure. 450 divided by 2 is 225. Now, 225 is not going to divide by 2. It's not an even number. It does divide by 3 because 2 plus 2 plus 5 adds up to 9, and that sum divides by 3. So 3 times something is 225. Let's use a calculator and find out what. 75. Now try dividing by 3 again. 75 is 3 times 25. And then at this point, hopefully you recognize 25 is 5 times 5. 2 times 3 times 3 times 5 times 5 is 450. So there's the prime factorization in exponential form. Next, number 41. We're given two numbers, 66 and 90, and we're asked for the greatest common factor. What is the greatest number that's a factor of 66 and 90? They both divide by 1, that's a common factor. They're both even, so they divide by 2, that's a common factor. Maybe they both divide by 3. But what is that largest number we can find that divides into 66 and into 90? There's two different ways to do this. One method is to list all of the factors of 66 and list all of the factors of 90. Then simply look for what is the largest one that's common to both lists. The second way, the way that the authors presented, is to do the prime factorization of each number. That's the way that I'm going to do the problem. So I'm going to start with 66, and I want to create its prime factorization. That's 2 times 33. And 33 is 3 times 11. 66 is 2 times 3 times 11. Now the number 90. 90 is 2 times 45. 45 is 3 times 15. And 15 is 3 times 5. So 90 is equal to 2 times 3 squared times 5. 3 squared is 9. 2 times 9 is 18. 18 times 5 is 90. Now we're looking for the greatest common factor. So first find what factors are common to both lists. There's a 2 in this list and a 2 in this list. What's the lowest power of 2 that's common in both? Well, there's only a single 2 in both lists. So common to both is 1, 2. Now there's a 3 in this list and in this list. What's the lowest power of 3's common to both lists? The first list only has 1, 3, and so that limits us to 1, 3 in our greatest common factor. Neither the number 11 nor the number 5 are common to both lists. 2 times 3 is 6, so our greatest common factor is 6. The largest number that divides into 66 and into 90 is 6. Next, number 43. The numbers are 182 and 196. And so with larger numbers like this, you can see why the author's method might be the better thing than trying to list all the factors. So let's do prime factorizations, starting with the 182. That's an even number, so for sure it divides by 2. 2 times 91 is 182. Now, does 91 divide by anything, or is it one of the prime numbers? If you have good notes, then you should have a list of prime numbers written out pretty far, like into the hundreds. And you'll see that 91 is not a prime number. So there is some number that 91 will divide by. It doesn't divide by 2, it's not even. It doesn't divide by 3 because 9 plus 1 is 10, and that sum doesn't divide by 3. It doesn't divide by 4 because it didn't divide by 2. It doesn't divide by 5 because it doesn't end in 0 or 5. It can't divide by 6 because it didn't divide by 2, but it does divide by 7. So with a calculator, a little bit of time maybe, you can get 7 times 13 is 91. And 13 is a prime number. So 182 is 2 times 7 times 13. Now let's do the number 196. It's an even number, so for sure divides by 2. On a calculator, 196 divided by 2 makes 98. Well, that's an even number. It's going to divide by 2. 2 times 49 is 98. Now here, if you know your times tables, then you'll know that 7 times 7 is 49. So 196 is 2 to the second power times 7 to the second power. Now we can get our greatest common factor. First, find what factors are common. Well, there's a 2 in both lists. What's the lowest power of 2 that appears in both lists? The first list only has 1 2, so our greatest common factor is restricted to only having one factor of 2. Now the number 7 is in both lists. What's the lowest amount of 7s that we can use in our GCF? Our first factorization only has 1 7, so that limits our GCF to only having 1 7. mean, you can't divide 182 by 7 to the second power. 182 doesn't divide by 49, right? But it does divide by 7, only a single 7. And so our greatest common factor is 2 times 7, which is the number 14. And finally, problem 45, the last one. The numbers are 330 and 945, and we're asked for the greatest common factor. We know how to do this problem by finding prime factorizations like in 41 and 43. Because of the size of these numbers, I want to do this on a calculator. So I'm going to go to Google Classroom where our calculators are linked. In the stream, here's the post that has some calculators. The calculator that I want is called the TI-84. I'm going to select that one from the link. Here is what a TI-84 graphing calculator looks like. You maybe have seen these in middle school or high school in classroom as a handheld calculator. Remember that right above the calculator, there's a little plus minus symbol that zooms bigger or smaller, and you can adjust it to fit on your Chromebook screen. Now, this calculator is able to do many things. What I want to find is a greatest common factor. That is a math operation. On the left side, there's a button called Math that contains a whole bunch of built-in math operations. I'm going to click the Math button. I'm going to be doing work with numbers. Across the top, you see some menu headers: Math, Num, Complex, Probability, and Fraction. I want the number menu, so I'm going to use the right cursor to go over to number. As you look down the list, you'll see some choices. Find the absolute value, round off the number, find the minimum, find the maximum. But that ninth one is greatest common divisor. Divisor is a synonym for factor. It's that ninth choice that will find the greatest common factor of numbers. So I can scroll down with the cursor and then select enter, or I can simply click on 9. Now on the screen it says, find the greatest common divisor of, and then in parentheses, I want to type in the numbers that I'm finding the GCF of. And I'm going to separate the numbers with a comma. Let's take a look at our numbers one more time. 330 and 945. Type them in. Separate them with a comma. The comma is its own button right above the 7 button. And 945. Close the parenthesis. On screen, I'm telling the calculator that I want it to tell me the greatest common divisor of the two numbers 330 and 945. Push enter. The number is 15. And so finishing up our homework, using the calculator to do it, the answer is 15. This concludes the lesson from Chapter 5, Section 1. Please turn in your notes and your line paper stapled together to the sub-teacher.